So now let's look at the general setup to finish off and actually do the general proof of Lagrange multiplier theorem. In general, we've got a map G from Rn to Rm, and M is the level set of G. Now, to make sure that's nice, what we would like to know is that C is a regular value, which means that for all x that satisfy this equation, dg is on 2. And in particular, let's pick out some point A that we happen to know is a constrained critical point. That's what we're going to be focusing on, and we want to show that there's something special about the relationship of f and g. But the main thing is that we want the implicit function theorem to be activated here. Given that that's true, what do we know? The implicit function theorem says we can pick some subset of the variables, n minus m of the variables, as free variables. This is exactly like the linear case with free variables and pivot variables. And then we can express the other variables in terms of those variables with a function, let's say little phi, which is smooth, differentiable, all the things you want. And then what you can do to make that slicker is to say, okay, what we really got is a parameterization. So call it big phi, capital Phi of x bar. So x bar lives in Rn minus m. And big phi takes that and uses these guys to parameterize the actual interesting surface living in Rn. So we've got this A, which is going to be the point of interest, which we're going to try to claim something interesting about Lagrange multipliers. A bar, you can't see the bar very well in here because I've decorated it. A bar is going to be the parameter version of that. So phi of A bar equals A. All right, so that's the setup we get from the implicit function theorem. And again, the crucial thing is we've got some other function, f. So f goes off to R, and we want to assume that this point is a constrained critical point. Most likely, we're interested in it because it's a constrained extremum. But really, it's more about critical points here. Well, what does it mean to be a constrained critical point? It doesn't mean that in all directions you get zero derivative. It means in directions along the this manifold, this level set, you get derivative 0. Or in other words, if I look at f composed with phi, and that automatically only gives me things that are on this set, then that should be an honest critical point, so that if I go in any direction here, the derivative is 0. Not any direction here, but any direction along the tangent space to this guy. Okay, so that's our setup. Now, what do we know? We know that phi, this is the crucial relationship between phi and g. Phi creates a point in that manifold, and then g has to send it to c, because the manifold is defined as the level set of g. And therefore, when you take derivatives, the derivative of g composed the derivative of phi is 0. And we're abbreviating that similarly to what we did before. This is going to be g, this is going to be a. So that's equal to 0. Now, for a different reason, this composition of derivatives is equal to 0. That's because f composed with phi is critical at this point A that we're interested in. So that's also going to be 0, but for a different reason. Okay, so as before in that second example, one of the crucial things is that this means that every output of A, or in other words, every column of A, is killed by G, or in other words, is when dot producted with the rows of G, you get 0. So one way to say that is the column space of A is sitting inside null space of G. Now you'll notice that I already went through this before. I had some sound problems on a previous version. We usually would just know, from this, we would just know that this is a subset inclusion. But what do we know about the ranks? The rank of G is equal to M. It's onto. That was the whole reason why we could be sure that this setup works out nicely, that this is really a smooth object, that it has a smooth parameterization, that the G and the phi fit together in the appropriate way. That means that the null space of G has dimension n minus m. So little n is the dimension of the null space. It's called the nullity of G. Okay, well, so that's the dimension of this subspace. Well, what's the rank of A? That's n minus m as well. That's guaranteed because phi is this nice map. Any nice parameterization map has a derivative that's 1 to 1. If you don't believe that, you can just look at the explicit form of this guy. Part of the derivative matrix of this guy is an n minus m by n minus m identity matrix. So it certainly has rank at least n minus m, and that's the biggest rank it can possibly have. Because these dimensions are equal, this really is an equality. So again, the crucial thing here is that, excuse me, if you look at G, if you look at the things that are perpendicular to the rows of G, that's not the tangent space of this surface. Here's the surface. Here's the tangent space. That would be C of A. Everything that's the image, let's go back to this picture. Right, the tangent space of this surface is the image of the derivative of the parameterization map. You look at all directions in here and you see where they go in the bigger dimensional space. That's the tangent space. Okay, so that's really crucial. This is really the tangent, oh, you can't see that, tangent space to M. Okay, we're not just saying that the null space of G, the things that are killed by the rows of G, is that plus other stuff. It's exactly that. And so that's the tight connection we need. So, and the rest of it is fairly formal linear algebra, but it's important to think about that second example as we do this, to think about the geometric relationship. So here's the relationship we have between A and G. Between A and F, we just have the inequality. And we wouldn't expect an equality. F is a function to R. It's got a big null space. It has to kill n minus 1 dimensions, and that's bigger than the dimensionality, usually, of the tangent space, the column space of A. But if we take this guy and take perps, that turns into, the perp of that is R of G. There's the perp of C of A. What about here? If we take perps, well, the row space of F is the perp of the null space. That, if the null space includes the column space of A, that reverses when we take perps. And guess what? Oh, that's R of G. Okay. So if I'm something in the null space of F, or sorry, in the row space of F, one way to express this is that that has to be something that kills all the outputs of A. That's really the expression that if I'm the gradient of F, the gradient of F has to be perpendicular to that tangent space. Otherwise, if it's at an angle, then I can go in generally that direction and get a non-zero rate of change and still stay on the manifold. Okay, so this expression is just directly saying that the gradient of F is perpendicular to the tangent space. But hey, wait a minute. The perp of the tangent space is exactly described by the span of the rows of G. That's that tight connection we get from the equality here. And that's really the deepest part of the fundamental theorem of linear algebra, is that the fact that you get certain equalities, not just one thing inside of another as a subspace. Okay, so the fancy way to say it is the row space of F is inside the row space of G. The more pedestrian way to say it is, look, this is a 1 by n matrix, and the row space is just that guy turned into a column vector. It's just a gradient, in other words. So that is in the span of the rows, and the rows of G are just the gradient of the constraint functions. So very, very explicitly it says the gradient of F is some linear combination of the gradients of G with some unknown coefficients lambda 1 through lambda m, and those are the Lagrange multipliers. There's the story. And I don't know, it might make some other comments, but that's really completes at least the proof of the main theorem.